in this talk, what I would like to discuss is a general topic, is the question of stability in geometric function inequalities. And actually, I thought that for considering also the duration of the talk, I will focus on one key example, also to motivate a question which I think, let's say a class of questions that I think are of importance. So so what is the question of stability? So the question of stability is the following. Let's say I have some function inequality. So I will have an inequality for which I can.
We cannot see. Oh yeah, now we can.
Oh.
Yes, all good.
Okay, we have an inequality for which equality cases are known. So you can characterize the cases where this inequality is an equality. So you know the sharp constant, you know the case of equality, so you know the minimizers. And then the kind of questions you have is that if.
Sorry, Alessio, there is again a problem. Oh yeah, there is always a delay.
Maybe there is a delay.
There is a delay between when you talk and.
It's very strange because also considering I'm just sharing directly on the screen, so it should. So let me see. So if the inequality, let's say, if a function.
Now it's good.
Or a set. So it could be a function if you're looking at, let's say, some function inequalities on space of functions like Sobolev, or a set if you're looking at isoperimetric inequality or Broomin-Koski inequality, stuff like that. So if a function set almost attains equality, is it close to a minimizer? So this is the kind of question. So are minimizers stable? Is it true that if I almost have equality, then I must be close to a minimizer? So I will describe everything, first this question, and then something further with an example. So the two Sobolev inequality, which is probably one of the easiest examples where this question makes sense, and you can also study it I would say with rather elementary tools. So what is Sobolev inequality? The Sobolev inequality says the following: if I have a function u in u, let's say, which is infinity and compactly supported in a Rn, and n is greater or equal than 3, then I know that the gradient of u in L2 controls up to a constant s the 2 star norm of u, where 2 star is the Sobolev exponent, 2n over n minus 2, and here s is a dimensional constant. And in addition, the equality case is known. So this S is known, the best S is known and is explicit. Equality, if and only if U is a multiple of a one parameter family of functions, U of lambda zeta, where so C is a real number, and then U of lambda zeta of X is the following, is n, there is a constant, n minus 2. Well, it doesn't matter too much this constant, but it's good to use it for normalization purposes. And then there is a lambda here, and then 1 plus lambda x minus z square to the n minus 2 over 2. So to have equality, you must be an element of this family. And just to give you the model example, so the model, let's say, function in this family will be u1, 0. So when you take lambda equal 1 and zeta equal 0, which looks like, so u1, 0 is like 1 over 1 plus x squared n minus 2 over 2. And then all the other functions are obtained by translating this function, dilating this function, and multiplying it by a constant. So these are the only equality cases. So now what is the stability question? So question, let's assume that I have a function u, that I have u such that, so I need to normalize some quantity. I will normalize the u, so I don't want u to be too small, I don't want u to be too large. So I will normalize it with the W12 norm, so such that the gradient of u in L2 is equal to the gradient of u 10 in L2, which is also equal to the gradient of u lambda zeta in L2. All these functions have the same L2 gradient. And also assume, so this is just a normalization, but the assumption is that there is this quantity delta of u, which is grad u in L2 minus Sobolev constant to star, which is, so this quantity is not negative, and assume it to be very, very small. And then the is u close to u lambda zeta for some lambda z. So this is the kind of question. Okay, so I normalize it. This normalization here is to kill, in some sense, this multiplicative constant little c. So because I can always multiply functions, so I normalize the size, and then I ask myself whether I'm close to one of these functions. So this is the answer to this question is well known, and actually there is a very clean result. So there is a theorem due to Bianchi and Egnell. This dates to 91, which says that under this normalization, what you have is that delta of u to the power 1/2 controls up to a dimensional constant c of n the minimum over lambda and zeta of the gradient of u minus the gradient of u lambda zeta in L2. Okay, so not only u is close, but you have it with a quantitative bound, and actually this is the best bound you can put. So this is sharp. Is sharp in the sense that this power here, 1/2, is the best power you can opt for, and also here you are controlling the right hand side with the L2 norm of the gradient. In some sense, this is the best norm you can opt to control, because your delta only involves the L2 norm of the gradient and the L2 star norm of the function. So you cannot opt more to control something more than in the L2 norm of the gradient. So this theorem is like the best you can opt for, both in terms of the quantity you have, in terms of the power. It has only a catch, which is the constant here, the Cn, is not explicit. It comes from a compactness argument. Okay, so the idea of proof is actually very easy. The idea is very easy because you just say, okay, assume, as I said, the delta of u is very small. Then by a compactness argument, more precisely by concentration compactness argument, so by compactness, let's say, you prove that your u, so here I can draw a family of functions m. This m is a manifold, is the space of u of lambda z as lambda z varies. So this is a m plus 1 dimensional manifold. The ambient space here would be W12. And so you say, okay, if my function u has small deficit, I can prove that u is going to be very close to this manifold. In particular, the W12 is an Hilbert space. So I can find an element on this manifold, u lambda zeta, such that u minus u lambda zeta is orthogonal to the tangent space at M at the point u lambda zeta. So instead you take the projection with respect where orthogonality is with respect to the W12 norm. So the gradient, the delta norm of the gradient of the function. Okay, so the norm here, these are the set of function phi in W12 with the norm grad phi 2 finite. So it's the closure of infinite compactly supported with this norm. So this is an inverse space. You can just take the closest element, the projection. Maybe it's not unique, it doesn't matter. You find a projection and then you prove that this is the right element. How do you prove it? You essentially, you go back to your inequality here, and you kind of Taylor expand this delta of u around this point. So here you have your delta of u, and you're gonna say delta of u is something like delta of u of lambda zeta plus this variation here, the variation I have. Let me call it phi, this small element. So by definition, and then you Taylor expand it, and you find an expression which is quadratic in phi. And then you have to prove that this expression will control your right-hand side, what you wanted to control. You need a bit of spectral analysis there to show that it works, but let's say it's not so difficult. So this is, in fact, the paper is very short. So why I chose this example? Because you see the question and you see an answer and you see how to get a sharp answer. Of course, then this question can be asked for many other inequalities. As I say, isoperimetric inequalities, Minkowski inequalities. This Sobolev inequality is not for p equal to. Precopalander, everything you want. The catch is that in any of the other inequalities, essentially, this strategy will never work. Because this strategy is really linked to the fact that you have a nice Hilbertian structure. You don't have that for the supermetric inequality, Minkowski, Sobolev inequality for p different than 2. Nothing like this will work. So it becomes a very delicate problem. But let's say for p equal 2, you have a clean answer with a short question. But already in this case, let me ask now a different question. So instead of looking at minimizer, I will look at critical points. So what is a critical point? Critical point is the following. Instead of looking for something which minimizes the Sobolev inequality, I will say, so I will consider the Euler-Lagrange equation. So I will say, let U be a minimizer first of Sobolev. Then what I know is that if I take the Sobolev functional and I do a variation, 1 u plus epsilon phi to star, and I differentiate this for epsilon equals 0, this will be 0. And then this must be true for every phi. You compute what this means. And this gives you a PD, which will be minus Laplacian of u equal some constant u to the p minus 1, where p is 2 star minus 1. Okay? And here c is some positive constant. So every minimizer satisfies this PD. Okay? And the question is, is this PD only satisfied by minimizer? The answer is no. There are solutions to this PD which are not minimizers. So this family of critical points. So these are critical points in the sense. These are the stationary point for the Sobolev inequality. The family of critical points, of course, is larger than the set of minimizers, but not if they are positive. So there is a famous theorem by Obata in 72, and also there is Didas, Lee Nirenberg, and Nirenberg in 79. So this proves that if u is positive and minus Laplacian u equals cu to the p minus 1, then u is, oh sorry, ci used the, well, okay, u is a multiple. So I should use alpha positive. Then U is of the form C of U lambda zeta. So U is a multiple of a minimizer. Okay, so the only positive critical points are the minimizers. Then you could ask yourself, question, assume that U is positive and minus Laplacian of U is equal to alpha U to the P minus 1 plus something little r, sorry, capital R, where R is small. So it's some small perturbation. Is U close to, let's say, U lambda Z? So here there is a relation, I should say. So this C depends on alpha. So for each alpha you choose, if you rescale U, you can this alpha will change. So if you take U and you multiply by a constant, this alpha will change. And then depending on this alpha, you will fix this parameter C alpha. So I'm gonna, so without loss of generality, I choose alpha equal alpha n such that C alpha equal 1. So I choose the parameter here for the PD, which corresponds to be exactly one of these U lambda Z. And then this is the question. So I solve almost the PD satisfied by U lambda Z, where R can be small in many senses to be decided. Is U close? And the answer here is no. So in this case, you don't have the stability. Why? Because there is what is called bubbling phenomenon. The kind of bubbling phenomenon you can do is just this. Just take two, let's say you take U1 zeta 1 and you take U1 zeta 2. So two bubbles with the same lambda. And you take centers. So zeta 1 will be the center of this, zeta 2 will be the center of this. And you take the 2 points and you start to move them very, very far away. As they move away, essentially the two functions will interact less and less. And since each of them is a solution of the PDE, when you compute, so if you take U to be U1 zeta 1 plus U2 zeta 2, they solve the PDE. So you have minus Laplacian of U is minus Laplacian of U1 zeta 1 plus U2 zeta 2. They solve the PDE. So this is alpha U1 zeta 1 to the P minus 1 plus alpha U1 zeta 2 to the P minus 1. But then this is very close to alpha U1 zeta 1 plus U2 zeta 1 to the P minus 1. And this is exactly little u. Why? Because since the two functions have almost disjoint support, the sum to a power is the same as the power of the sum. The error you have is in the support. Of course, the support is everything. But since one is super small, where the other one lives and vice versa, the interaction here is very small. So they're almost solutions. And you can do this with as many bubbles as you want. Also, you could also play not with the centers, but with the lambda parameter. So you could take also functions like this. So this will be U lambda zeta 1, where lambda is very, very far from 1, either going to 0 to infinity. And then the two functions will interact very little again. So there are many ways of building approximate solutions. However, this is essentially the only way. So there is a theorem due to Struve, 1984, which is like the compactness version of the statement. It says the following. So let's assume that the gradient of U square is bounded by, let's say, L plus 1 half, where L is some integer number. So why do I need this assumption? The reason why I need this is because I can take solutions of Sobolev and start to construct examples as the one I just described here, with adding as many functions as I want. So a priori, let's say approximate solutions, I could have countably many of these bubbles. if I put the right weights. That's not good. So what Struve did is that say, okay, let's fix some quantity. He fixed the total, let's say, energy. This is the W12 norm of the function. Let's fix it in such a way that this number L becomes an upper bound on the number of bubbles I can use. So this will become like an upper bound. And then it says, then for every epsilon, there exists delta epsilon, such that if delta of u, what is delta of u here? Delta of u is minus Laplacian of u plus alpha u to the p minus 1 in the dual W12 norm. So it takes the negative Sobolev norm. So this is the dual space of W12. This is the natural space. I don't want to enter now why, but it's really the natural space where you want to measure the error. And if this quantity is less than delta epsilon, then gradient of u minus a finite sum of bubbles, lambda I zeta I, into is less or equal than epsilon, where m is less or equal than L. So there exist finitely many bubbles such that I'm very close to that in W12. So this is the equivalent of Bianchi, not of Bianchi-Egnell, of just a qualitative version of Bianchi-Egnell. So there is no quantitative bound, but with finitely many bounds. This is the theorem that's Struve proved. And then the question is, can we get a quantitative estimate? Oh, sorry, here I should, this is not correct. I realize it now. This times the Sobolev constant to the n. So if you use, sorry, with this choice Sobolev constant to the n, this is going to block the number of bubbles. Okay, and then the theorem, there is a, so this was proved first by, so there are three theorems. Ciraulo, myself and Maggi in 2017. Then myself and Glaudo in 2020. And then Deng, Sun, and Wei in 2021. There is the following. Under Struve assumptions, so you block this. Then A, if L equal 1, so if there is only one bubble, then there exists, so I say, well, it's clear that it exists. So delta of u with a constant controls gradient of u minus gradient of u lambda zeta for some lambda and zeta. I will comment in a second. B, L greater than 1, dimension between 3 and 5, then Cn delta of u controls gradient of u minus a sum of bubbles. So like Struve, C, L greater than 1, N greater or equal than 6, then, 1 second, I need to just, I wrote down myself the power because now it's tricky. Yeah, so Cn delta of u greater or equal than, sorry, the other way around. So I should say gradient of u minus the sum up to m of the gradient of bubbles is less or equal than, up to a constant, delta of u square root of log delta of u if n equals 6, and delta of u to the power n plus 2 over 2 n minus 2 if n is greater or equal than 7. And that's the theorem. So, and these theorems are sharp. So theorem A corresponds to Ciraulo-Figalli-Maggi. Theorem B corresponds to Figalli-Glaude. Theorem C corresponds to Deng, Sun, and Wei. So these are the three authors. It's interesting here. You may notice that the power is 1. It's not anymore 1/2. So this is a natural for critical points. For problem with minimizer, you get a 1/2. For critical points, you get power 1. Although the power 1 fails at some dimensions. So these problems are very natural, and I would like to conclude with this statement. Why? Because very often when you look, for instance, at the PDEs, you naturally find, so when you look at the evolution PDEs, like this problem was motivated by the so-called Yamabe flow, you have maybe an equation, a parabolic equation, dTu equals something, and then you have an entropy, a quantity which decreases along the evolution. And then you have the derivative of the quantity that decreases along the evolution, which is less or equal than 0, but not only, it's equal to some quantity which is negative. It's like a dissipation. Okay, so there are always the equations like d over dt of the some energy equal minus some dissipation. And if you do the Yamabe flow and you choose suitably the energy, this dissipation will be delta of u, where delta of u is this quantity. So being dissipation close to 0 means being almost a critical point of Sobolev, of the Sobolev inequality. And so this gives you information. It's telling you either you have your energy, which you are dissipating in evolution, dissipates at some rate, it dissipates, let's say, fast, or whenever the dissipation gets smaller, it means that you're very close to some model situations. Something is happening. And there is a geometric counterpart of this, if you look at the isoperimetric inequality, which will be the mean curvature flow. So the kind of, the analog of this for the isoperimetric inequality will be minimizers of the isoperimetric inequalities are bold, and then critical points will be constant mean curvature, and is known by Alexandrov theorem that surface with constant mean curvatures are spheres. So there is a perfect counterpart to this theorem in the isoperimetric world. Isoperimetric inequality, constant mean curvature surfaces. And also there you can have bubbling. So having mean curvature almost constant doesn't mean that you're a sphere. You may be close to a union of spheres. And actually the counterpart of this for the mean curvature case is still open. There is not such a result known. I mean, there are results, but no sharp. So this result is sharp. All the statements are sharp and the powers are sharp. So that's why this is a rather conclusive result that I thought it was also a nice motivation, not only for this setting, but I think for many problems where it's very natural not only to look at minimizers, but critical points. So I think my time is over. So I thank you for your attention, and please ask any questions. Thank you.